Okay, let's look at 15.7. The first one I'm going to look at is number 10. It says find the local max and mins and saddle points. If you have three-dimensional graphing software, which we do use Maple, graph the function with the domain and viewpoint and reveal all the important aspects of the function. Okay, so let's do this one by hand. Let me just go through and take the derivatives. Now, if this is equal to 0, then we have that. So that shows us that either y is 0 or x is negative 1. We take those values and plug them back into here. When x is negative 1, we have f of x negative 1y. That's going to be 6 plus y squared minus 10 equals 0. We get y squared equals 4. Y equal plus or minus 2. So we get the points negative 1 plus or minus 2 for critical points. When we plug in y0, we get 6x squared plus 10x equals 0. Factor out a 2x. We get x equals 0 or negative 5/3. So we get the critical point negative 1, 0, and negative 1, negative 5/3. No, y is 0 here, sorry. We get the point 0, 0, and negative 5/3, 0. Okay, then find out what capital D is. We do f of xx. Okay, then we plug all the points into D. And that's less than 0. This is going to be the same thing. So these two are saddle points. At 0, 0, we get 20 minus 0, that's greater than 0. And f of x, 0, 0 is 10, that's greater than 0, so that's a local min. And minus 5/3, 0 is minus 10 times minus 4/3, and that's greater than 0. And the second derivative evaluated at that point is less than 0, so that's a local max. Okay, now we're going to go to Maple. And graph this. And I want to do with plots. And I want to plot 3D. 2 times x cubed plus xy squared plus 5x squared plus y squared. And I'm going to go from negative 3 to 3 because all my critical points will be in that domain. And then we're going to box the axis and turn it around. And you can see when x is well, x and y are 0, 0, we have a low point right here, 0, 0, 0, 0 is right there. And we have a high point, this is about negative 5/3 is our high point right there where the arrow is. There's a little bump right here. So at negative 5/3, when x is negative 5/3, there's the local max. When x is 0, there's the local min. And we can turn that around and see better if you want, so that we can see a low point, the valley, and the mountain. Okay. Let's go back to our discussion. Let's look at number 20. Okay, and 20 says, use a graph or level curves to estimate the local max and min and saddle points, and use calculus to find these points or values precisely. So 20 is f of xy, xy e to the minus x squared minus y squared. And, okay, first I'm going to use maple. And again, I need width plots. And I'm going to plot 3D. X times y times e is exp. And I'm going to go from -2 to 2. And if that's not good enough, I'll have to change it. Oh, well, that's a really good picture. We see some mountains, and we see 2 mountains and 2 valleys, so we should expect 2 maxes local and 2 local mins here. I'm going to box the axis so you can kind of see. So let's look at x. Right here's a local max, and we're going to say that that's around 0.8 right here. Watch the arrow. And this is a local max, and that's about negative 0.8. So let me write that down. We have a local max at, I don't know the y value yet. X is approximately 0.8 and negative 0.8. And we have mins. There's a min right here. And again, that's when x is a negative 0.8 and, let me turn this around, and about a also the same thing at negative 0.8. We have so the y values are going to be different. So local max, x is about a 0.8, y is, again, we're just estimating this, Let's turn this around. Okay, so x is 0.8, y is 0.8. And when x is negative 0.8, then y is about, okay, it's right here, so y is about a 0.8. It's right there. Y was about a 0.8. And z was about 0.2. We'll go back and look at that. I messed this up. Okay, so let's turn it back to x. The highest it goes, it's upside down. There it goes. The highest it goes right here. Watch the arrow is about 0.2. So z is about 0.2. It'll be the highest it goes. And the lowest it goes is negative 0.2. So the mins are when x is negative 0.8 and y is negative 0.8. Z is about negative 0.2, and when x is about 0.8, y is about negative 0.8, and z is about negative 0.2. Okay, so those are our guesses for max and mins locally. Let's look at settle points. And there looks like there's a settle point right here at 0, 0. See right here where the arrow is, when you move it around, it's like you could sit on it. It's a saddle. So if you look at it like that, you can see that 0, 0 is probably a saddle point when I look right here at 0, 0, that middle point. Okay, now we're going to have to prove all this. And I'm going to do it the long way, but I'll show you how Maple can do it really, really quickly. So this is a pretty long problem, but f of x, if we take the derivative, I'm using the product rule. And the function really is this. So I'm going to use that as my first function and that as my second function. So I'm using the product rule right here. And f of x is going to be okay, and if I fix this, I can factor everything out and get 2x squared minus 3. Okay, f of y, I'm doing the same thing, the product rule. F of y. Okay, that's the product rule with respect to y. And then the second is going to be this. Derivative e is itself, then you come back and take the derivative of the exponent. All right, when you fix this, you get this. Okay, f x y, that means first you take with respect to y, then x, that's going to be minus 2. So I'm using the product rule there too. All right, if we set f of x equal to 0, we have y times minus 2x squared plus 1 All right, that tells me that y0 or x is plus or minus 1 over the square root of 2, because e's never 0, e's always positive. So we set that equal to 0 or that equal to 0. Then when we move to f of y equals 0, we have pretty much the same thing, just opposite. So that's always positive. So we get x equals 0 or y equal plus or minus 1 over the square root of 2. So this gives us our critical points, 0, 0, and plus or minus 1 over the square root of 2 plus or minus 1 over the square root of 2. Now notice 1 over the square root of 2 is 0.707, and we guessed ours to be about 0.8. So that's a really, really good guess. We're really close, and we guessed 0, 0 to be a saddle point, so we're going to prove that. So remember what D is. D is f of xx. So that's going to get squared. We're going to have two of those. And then we're going to have minus f of x, f of xy squared. Okay, well, if we're wanting the signs, whenever you square anything, that's going to be positive. That's going to be, well, e to any value, we can just squared. When we take that out, that's going to be positive. So that's not going to have any effect on the signs. So D of 0, 0, we're testing the critical points. It's going to be 0 minus 1 times either the 0, which is negative 1. That's less than 0. So that proves that 0, 0 is a saddle point, which we guessed when we looked at the picture. So we were right about that. When we test this point, by plugging it in to our formula, because this is 4 minus 0, so that's positive. Okay, so let's just keep going. Let's do all the d's first. And the same is going to be true for negative, because you have x and x, so x and y, and negative, negative, positive. That's going to be positive. I'm looking up here. Let me do it in red. That's going to be positive. It's the same thing as squaring it. That's squared, so it's going to be the same as before. That's squared, same as before. Squared, 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 squared. So this is going to be the same as the one we just did. That's going to be 4 minus 0 also, which is greater than 0. All right, then we have d of 1/2. No, let's do the minus on this first. That's going to be greater than 0. And same for this one. If you look at the symmetry of the equation, it's going to be also greater than 0. Because again, look at the red checks. If x is equal to y, which pretty much they are here. So if you reverse them here, it's just going to be the same as if these are reversed. So they're all positive. Now all we have to do is check to see if they're local max or min. We have to check fxx at those points. When we plug it in, we get 1 minus 2, which is less than 0. So 1 square root of 2 over square root of 2 was a local max, which is what we guessed. We guessed 0.8, 0.8 to be a local max. And the same for, since x is squared in that equation, that's also less than 0. If you look at the equation, let's go back and look at f of xx. It's down here. right here. When x is equal to y, okay, we don't care about that because that's positive. E is always positive. X times y, and x is equal to y, so that's going to be squared, so that's going to be positive. And x squared there, if x is negative, is going to turn positive. So the equation kind of has some symmetry to it. So that saves us time when we do this. Then f of x of 1 over square root of 2, negative 1 over square root of 2, is negative 1 minus 2. Okay, this is times, which is still less than 0. But that's greater than 0. And same for this, again, because f of x has kind of symmetry in the equation. When x is equal to negative y, that's going to be greater than 0. So this says that that's a local max. So these two are local maxes, and these two are local mins, which is what we said right here. Local maxes and our local mins. Wait a second. Oh wait, let's look at this again. What did I say up here? Let's go back to Maple. Our maxes were at, okay, right here. That's where y is negative 0.8 and, let me see, x is negative 0.8. Okay, I think I wrote this down wrong. This should have been negative. Okay. I have those signs wrong up there. So that's when they're both positive and when they're both negative. And that's what I got when I did this test. Let's see, where's, okay, there's number, oh, right here. Okay, so that's what I have. Remember, 1 over square root of 2 is about 0.7. We said 0.8, but that checks out with our graph. All right. Now, also when we use Maple, let me go back to Maple. We got this picture. I want to define my function here and take the partials and save us some time. So what you can also do, although you need to also know how to do it longhand, let me define f, or little f, as a function from x, y, and our function was x times y times exp negative x squared minus y squared. And I want to take I want to differentiate f of x, y with respect to x twice. So this is f of xx. See how simple that was? Instead of doing everything we just finished doing, if we simplify it, it factors it for us. So let's call that, just because I'm going to use this to find capital D, let's call this A. And let's do with respect to y. And let's call that b when we simplify it. And then let's differentiate f of x, y with respect to y, and then x, or x then y, doesn't matter because it's continuous. And we'll call c the simplification of that. Remember, percent does what your previous command was. And if you check what we did longhand, that's what we get on all those cases, if you go back and do that. Now, I want to define t as f of x times f of y minus f of xy squared. So that's like the D, our big capital D in the text. And I could simplify that if I wanted to. Now, if I want to plug in my critical points, it's really easy. I can just say evaluate t, and our critical point was 0, 0. Let's try that one first. X equals 0, y equals 0. And I get negative 1, which is less than 0, so that says it's a saddle point, which is what we got before. And we can evaluate t at the other critical points, 1 over the square root of 2, and y equals 1 over the square root of 2. Okay, I missed a parentheses. And e is always positive, so that's 4. So that tells us that when I plug that into capital D, I get positive. And I can do that with all the others. We're just going to copy and paste. Wait. Because all I'm going to do is go back up here and change my signs. Let's make them both negative. Okay, here make y negative, and here make x negative. So I get all my critical points plugged into capital D. And so capital D is all positive no matter what critical point we plug in with the 1 over the square root of 2 for x and y, positive or negative. And then we have to do f of xx, evaluate that, but we called that A, so we want to evaluate f of xx at the critical points. And that's a negative value. E to the power is always positive. So that's negative. So that tells us that when D is positive and f of xx is negative, we have a local max. And we're going to copy and paste that again 3 times. Delete, insert. All right, let's evaluate f of xx at these critical points. So there's 4. I'll go back and change the signs on x and y so we get each critical point. And then let's go back and... Alright, so since d was positive in all the cases, then we move on and check f of xx, which is we called a. And in the first two cases, it's negative, so we have local maxes. And in the second two cases, we have local mins. And that's what we got when we did the longhand, but it was a lot longer, as you can see. So Mabel helps us out a lot on evaluating things that it takes us a long time to do on paper. All right, let's go back to the homework and look at 30. And 30, our function was, or is, and we wanted it to be constrained on this domain. So that's a rectangle. 0 to 4, and y is 0 to 5. So we have this rectangle, and their endpoints are 0, 0, 4, 0, 4, 5, and 0, 5. So we have to check those. The first thing we're going to do is find f of x, and set that equal to 0, and f of y. So we'll find our critical points this way. Here we get x equal 2, here we get y equal 3, so the point 2, 3. Let's look at our boundaries. We have boundary 1, boundary 2, boundary 3, and boundary 4. On boundary 1, we have y equals 0. So we have f of x 0 is 4x minus x squared. And we take the first derivative. Set equal to 0, we get x equal 2. The second derivative is negative, so that is a local max. So f of 2, 0 is something that we need to check out. And or 2, 0 is a critical point. On boundary 2, we'll check the boundary points. We have x equal 4. That's the equation of that line. So f of 4y is 16 plus 6y minus 16 minus y squared. So the first derivative is 6 minus 2y. That gives us y equal 3 as a critical point. Second derivative is negative, so that's a local max. So then we have the point 4, 3 for a critical point that we need to check. And again, we're going to go back and check the boundary points. On boundary 3, we have y equal 5 is the equation of that line. So let's see, this is get x equal 2. Second derivative is negative. So we have a local max there. So we need to check the point 2, 5 as a critical point. And on boundary 4, that's the y-axis, x is equal to 0. So f of 0y is 6y minus y squared. We get y equal 3, so we need to check 0, 3 as a critical point. So let's check all these values. F of 0, 0 is a boundary point, that's 0. f of 4, 0 is a boundary point. When we plug that in, we get 0. F of 4, 5 is 30 minus 25, which is 5. F of 0, 5 is 5. Okay, those are boundary points. Now, critical points, we have f of 2, 3, which is 8 plus 18 minus 4 minus 9 is 13. And then we have f of, let's go back and look. Okay, 2, 3. We have 2, 0, and 4, 3 we need to check. 2, 5. We also have 2, 5. So f of 2, 0 is 8 minus 4, which is 4. F of 4, 3 is 18 minus 9, which is 9. F of 2, 5 is 8 plus 5 minus 4 is 9. And we have f of 0, 3, which is 9. So the absolute max is at 2, 3, and the maximum value is 13. And the absolute min is at these two, because that's 0 is the lowest value in all these. So absolute min is at 0, 0, and 4, 0. Okay, and I think that was what they wanted, was the absolute max and min. Okay, now 48, we have a slate bottom, an aquarium. This is the height, the length, the width, and this is slate on the bottom. And slate's 5 times as much, so the cost is going to be 5 times the length times the width. Plus we have two sides that are W and H, and we have two sides that are H by L. And we have our volume to be length times the width times height, but that's equal to a constant. That's fixed. So if we solve this for H, we have K over LW. So our cost function is 5 LW plus 2K over LW times L plus W. And that's 5 LW plus 2K times 1 over L plus 1 over W. Okay, so cost with respect to L is 5W minus 2K over L squared, which equals 0. So W is 2K over 5L squared. And CW is 5L minus 2K over W squared. And we're going to take that and plug that in here. So factor out of L. We get L equals 0, which doesn't give us anything, or L is the cubed root of 2K over 5. So that's one of our unknowns. And then we plug that back in here for W and do some work. We get W is 2K over 5 times 2K over 5 to the 2/3. When we simplify that, we get the cubed root of 2k over 5. Well, L is equal to W. Then, since we know the volume is length times width times height, and that's equal to K, we know H is K over L times W. If we substitute these back in, we have K over 2K over 5th, that's the 1/3, and then we square it, so that's to the 2/3. And when we simplify that, we get K to the 1/3 times 5/2 to the 2/3. Now we're going to check this. So CLL is 4K over L cubed. CWW is 4K over W cubed, and CWL is 5. So D is 4K over L cubed times 4K over W cubed minus 5. And when I plug all these in, I get 16K squared over, when I know L and W, I'm going to plug them in here. I have 2K over 5, because that's cubed root cubed. Then that's going to be 100 minus 5, and that's greater than 0. So then we check CLL at the point and L is equal to W. So at the point that's going to be greater than 0, so we do have a local min at that point. We want to minimize costs, so that's what we want to do, and we check that. So we have all our dimensions. Let's go back and let's circle them. We have L here. We put that back into W. We get L is equal to W, so that's what W is. And then when we plug it into H, we get this for H. So those are the dimensions that will minimize the cost. Okay.